Hi, my name is Simon Delord. I am a solution architect at Red Hat, and today I would like to talk to you about data streaming and microservices-based architectures for OT environments. This session has both a conceptual, high-level view of what OT and its challenges are, as well as a quite detailed technical component. As such, if you're more on the technical side and familiar with OT and its challenges, I would recommend that you jump to the demo section around 10 minutes into the presentation. Otherwise, let's proceed with the rest. In this presentation, I will talk about operational technology or OT, what it is, and what challenges come with such environments. I will then go through an example of how Red Hat can offer innovative and secure solutions to address several of those challenges, and I will illustrate it with a live demo. Let's dive into what OT is and what challenges it faces. Operational technology, OT, encompasses the hardware and software used to monitor, control, and improve the performance of industrial machinery and operations within production environments. It enables real-time data collection and informed decision-making, forming the backbone of asset, process, and system management. OT is fundamental across industries such as manufacturing, mining, oil and gas, and utilities, and includes equipment and platforms like programmable logic controllers, or PLCs, distributed control systems, DCS, and supervisory control and data acquisition, SCADA systems. The foundational reference for structuring and securing operational technology environments is the Purdue Model, also known as the Purdue Enterprise Reference Architecture. It describes a hierarchical structure of industrial systems, organizing them into layers that separate business operations from plant-level control. At the top, level 4 and 5 represent enterprise functions such as planning, resource management, and corporate IT systems. Level 2 and 3 encompass plant-wide supervisory systems, including historian database, HMI application, and SCADA platform that interface with the field. Beneath these, Level 1 is home to basic control functions powered by PLCs and distributed control hardware, while Level 0 covers the physical process itself, sensors, actuators, motors, and instrumentation that interact directly with the production environment. The benefits of the multiple layers in the Purdue Operation Technology Model are to, first, enhance cybersecurity by providing effective network segmentation. Secondly, containing incidents and risks by isolating critical real-time control systems, level 0 to 2, from enterprise-level business systems, level 4 and 5. Delays or disruptions in the IT network do not impact the stable and continuous operation of the physical processes. If we now look at an example of a high-level OT architecture, I have taken an example in the mining sector to make it more real, but this would also be applicable to other industries. In this example, we have multiple OT sites representing multiple mining locations. At each site, there is a fleet of fixed endpoints as well as a fleet of mobile endpoints, typically trucks. All endpoints, as per the previous slides, send information to one or more systems on site. There is a mix of transmission technologies, for example, wireless or fixed networks, but also a set of aggregation functions. MQTT as a technology is quite common there, allowing the many endpoints, we're talking about hundreds or thousands or even more, endpoints to send the data to what's typically a monolithic application with a database, presented here as local systems. Those local systems may then need to export or present data to systems sitting in the wider IT environment, and do this through a DMZ or demilitarized zone. Now, what we can see from the previous slide is that today's OT environments face significant challenges that stem from how many solutions have been deployed over time. This has often been done in isolation with different vendors for different systems, and each of them deploying additional proprietary hardware or software. Furthermore, those platforms are built using monolithic architecture, which makes them slow to evolve and difficult to integrate. Again, equipment like trucks and sensors commonly use proprietary protocols, locking organizations into specific vendor ecosystems. The data is often centralized in production databases, and while this keeps operations running, it makes access risky and complicated. As a result, External systems such as IT, cloud analytics, and optimization tools struggle to connect, and even within the OT stack, interoperability is limited. For example, fixed and mobile fleets cannot easily communicate. Finally, with so many devices and systems now in place, managing the environment has become increasingly complex, and this fragmentation poses a real barrier to future data-driven initiatives. Let's now look at how Red Hat open source and cloud-native solutions can address several of the challenges presented earlier. This is a busy slide, but what I have done here is added in dotted lines the environments where the Red Hat technology stack can be deployed. It relies on two main components that are OpenShift and the Red Hat supported version of Kafka, IMQ streams. The deployment of OpenShift and Kafka in the OT, DMZ, and IT environments provides a consistent architecture that addresses the current OT challenges. First, as fixed equipment or the mobile fleet sends messages to the local database systems, typically through an aggregation or brokering layer, often MQTT, the Debezium connector functionality, which is part of the Red Hat IMQ Streams ecosystem, is able to provide access to this jailed data by exporting it to Kafka. This is done without impact to the existing OT applications and can be then, still in full compliance of the Purdue Model, exposed and consumed by other systems located either in OT or IT. Next, Red Hat also provides a set of simple connectors to integrate the various siloed systems. For example, it is possible to provide event-based communications between the fixed fleet and the mobile fleet, and hence address the difficult interoperability between those solutions. Finally, those Red Hat supported technologies like Kafka, Kafka Connect, and Kubernetes OpenShift are critical because they give organizations a production-grade foundation for OT that is secure, resilient, and fully backed by enterprise support. While open source projects and community components are valuable for experimentation, they introduce risk when placed into mission-critical environments, particularly where uptime, security patches, and long-term lifecycle stability are mandatory. Red Hat provides tested, certified distribution, hardened container images, lifecycle management, regulatory-aligned security updates, and a guaranteed support at SLA. This means that when something goes wrong, for example a bug, CVE, performance regression, connector failure, cluster outage, the business has a vendor that is accountable, responsive, and contractually committed to resolution. Now, if we dive a little bit deeper into OpenShift and Kafka, OpenShift provides a resilient, scalable, and secure foundation for running both containers and virtual machine at enterprise scale. In parallel, Kafka delivers a highly resilient and scalable approach to streaming data across the organization. Kafka's publish and subscribe model, combined with guaranteed delivery, ensures that information flows reliably between systems without loss. Both platforms are built for resilience, with OpenShift using multiple control plane nodes and Kafka operating through clustered brokers to maintain availability. They also scale independently. OpenShift expands its data plane capacity as workloads grow, while Kafka brokers can be added to increase throughput. Together, they support true multi-tenancy, allowing one or many Kafka clusters to run on OpenShift with multiple tenants per cluster, each securely segmented from one another. This provides a flexible, Purdue-compliant, high-performance foundation for OT application at scale. And before we get into the demo, I would also like to quickly talk about the operational benefits of this approach. By combining the orchestration power of OpenShift with the scalable streaming capabilities of Kafka, it is possible to centrally manage highly distributed OT environments. OpenShift provides a consistent, automated platform across multiple sites, from edge to data center to cloud, ensuring that workloads, policies, security controls, and upgrades can be deployed and governed from one place. Kafka complements this by acting as a resilient, fault-tolerant backbone for real-time data movement, allowing events from remote assets to flow into a unified platform when they can be processed, analyzed, and acted on at scale. Together, they provide one cohesive control plane for operations, reducing fragmentation, improving visibility, and enabling organizations to run distributed systems as if they were centrally located. It is now time for the demo. For the demo, I am only showing a single site, but the same patterns can be extended across multiple sites. There is a database that is holding all the information about the truck, MySQL in this case, but it could be any other type of databases like Microsoft SQL, PostgreSQL, for example. As part of the demo, I'm going to cover OpenShift and the OpenShift console, the Kafka environment on OpenShift, the Kafka connector called Debezium that tracks changes in the MySQL database and publishes them on Kafka. I'm also going to present an external Kafka client. I have chosen Grafana in that case as an example to display the routes of various trucks across multiple display windows. Another connector linking Kafka to MQTT to simulate an event-driven function. For example, based on the truck location, I am able to notify a fixed endpoint like a crusher or vice versa. So we will see the MQTT to Kafka mapping as well. All right. I am now connected to my OpenShift cluster via the web console. I'm going to show you the various components of the demo. As you will see, most of the software components here have been deployed using operators. Kubernetes operators are software extensions that automate the operation of complex applications running on Kubernetes, going far beyond basic deployment to manage ongoing tasks such as scaling, upgrades, configuration, failure recovery, and lifecycle management. Inspired by the knowledge and actions of human operators, they encode operational intelligence into the platform itself so applications can run reliably without constant manual intervention. This is especially important for distributed systems like Kafka, databases, or middleware, where configuration and state must remain consistent even as workloads evolve. Operators reduce operational risk, eliminate repetitive maintenance work, enforce best practices, and ensure that critical applications remain healthy and up to date in production. In short, they transform Kubernetes from being just a container scheduler into a full application lifecycle platform. So, if I go into the Operator tab, and if I look for Grafana, for example, Grafana comes to OpenShift as an operator and can be deployed and configured by the click of a button. Similarly, if we look at databases, there are many to choose from. So if I now look at the installed operator in my environment, if we focus on the Kafka component called streams for Apache Kafka in Red Hat, I can see that both the Kafka clusters and that web console to monitor it have been deployed using an operator. Looking more deeply into Kafka, there are multiple components of it. The first is the cluster itself of kind Kafka, and then we also have a set of connectors of kind Kafka Connect and Kafka Connector. You can see on this tab the status and other information about all those elements. Now, if I look into more details around the configuration of the connector, what I mean by that is the component looking at changes in the database and publishing them onto my Kafka broker. I can see that it is represented as a single YAML file, right? With all the information in it. Now, for example, if we look at line 109, 110, I can see the tables and columns monitored within my environment. And if I ever need to start tracking other columns or new tables, I can simply add them here. Now, let's look more into what this broker looks like on top of OpenShift. So if I look at the actual implementation of it, we can see here all the pods running in my environment. At the top, you can see the Kafka control planes and brokers that are resilient. There's multiple of them, 3 of them. And then if you look below, you can see that the Debezium connector, the Grafana deployment, the Kafka console, and finally, the actual database. I've put everything into the same project called Debezium example at the top for simplicity. But obviously, those various components could be sitting in different projects, right? In OpenShift, projects are the fundamental unit of organization, isolation, and resource management. They act as secure, namespaced environment where users can deploy applications, services, configuration, storage, and pipelines, all with their own access control and resource quota. I am now going to show how the traffic is going through the environment, from the database to the various elements of the demo. First, let me connect to the Kafka console. All right, I'm in the Kafka console overview, and I'm going to look at topics. In simple terms, a Kafka topic is like a named feed of events. Producers publish to it, consumers subscribe to it, and Kafka stores it reliably for scalable streaming. For the demo, the connector, the Debezium connector connecting to the database is a producer, while Grafana, for example, is a subscriber retrieving the data from this Kafka topic. All right. In this demo, there are many topics, but the one of importance for us in this demo is the real-time trucks location topic. It shows in real time where trucks are located on the mining site. Another interesting one is called the truck schema history. As database scheme evolve over time, typically a change of name for a field, adding and removing columns, etc., Debezium is able to track changes to a specific table by capturing data, changes, and schema modification and publishing them as events to Kafka. So now if we look at this topic, I can see there are a lot of messages available, and I'm going to expand and look at one of them. I'm taking the latest one, and in the latest one, I can see on the right-hand side the content of the message and the information about the truck ID, truck number 2, and its latitude and longitude. Now, let's look at another way of displaying this information using Grafana. I am now in the Grafana web console, and I can first inspect the type of data sources. As you can see, I've created two sets of data sources for it, one based on MQTT and another one based on Kafka. In the Kafka one, I've provided the configuration, like which Kafka broker to connect to, what authentication mechanism am I going to use, which topic should I be listening to, etc., etc. Let's now look at the actual display of the truck routes on the site. So I'm going to go into the dashboard function, and if I look at the truck maps, as you can see, it now displays in real time the information it's getting from the Kafka topic. I have put here a basic map display, but we could use something more advanced like Google Maps, for example. It is tracking two trucks, same color. So this setup shows that data that would normally be jailed within a specific application, a SQL database, can then simply be exported into a Kafka environment and then into any type of client who can access the relevant topic. And if we wait for a few more seconds, you will see the route of both trucks around the environment. Before I get onto some of the performance view of Debezium and also the integration between Kafka and MQTT, I'm just going to share now how I am generating the current traffic on the map. I've just written a simple Python script located in this Git repo that's shared as part of this presentation. And this Python script generates various routes for a couple of trucks. The script injects at a regular interval of every few seconds the location of a couple of those trucks into the database. The Git repo also contains all the information for all the demo elements that you are seeing, so please feel free to browse through it if you would like to recreate something similar. And I'm now going to focus on the monitoring and observability of the solution. So if I go back to my OpenShift console and I look at the observability functions onto dashboards, and I select the information I'm interested in, which is the consumptions per pod for the Debezium component, I can see that OpenShift comes with a set of predefined dashboards used to monitor all the components on the platform. Remember about the project concept I was talking earlier, I have now full visibility on it through the console. If I scroll down, I can see the CPU, memory, networking, and storage metrics for all the pods in the Debezium example. As you can see, the blue line is the connector, the Debezium connector, and the pink one is the database one. Those metrics have been stable for quite some time, and I can even expand the time range to see over a longer period of times too. So if I go back here and look at expansions over the last week, for example, I can see the trends across my environment for longer periods of time. To finish the demo, I'm going to show the Kafka to MQTT ease of integration. As we have seen in this presentation, because of the way different applications and solutions are deployed in OT, it is often quite challenging and difficult to integrate them together. For example, I may want to be able to send notification from my fixed fleet environment to my mobile fleet environment or vice versa. So let's have a look at this. I'm now going into a different project called MQTT. Remember, this is to provide separation within my environment. As you can see, there are several pods running here. One is the MQTT broker called mosquito-769774, etc., etc. Then I have a simple MQTT listener, effectively a consumer to a specific MQTT topic. And I also have created another connector called the Kafka to MQTT bridge, right? This function here is able to extract data from the Kafka topic onto which Debezium is publishing. It picks it up, it's effectively a consumer, and then it pushes it into the MQTT environment. As you can see, we track the message IDs and the information associated with it. Now, if I go back to my pod in the project, and I look at the listener, and I look at the logs, I can see now that the logs of this MQTT listener, I have received information about the different trucks and their respective location, giving you the truck number, the latitude and longitude with the message ID, not the truck ID, sorry. That's it for the demo part. Let's finish this presentation. Okay, so what have we seen today? We have seen that Red Hat technology can provide access to data without impact to the existing applications and allow future growth in analytics, both in volume and complexity. It also allows OT systems to easily interact with each other, for example, fixed mobile fleet integration. We also provide an open source and interoperable solution to integrate with proprietary protocols and solutions. Finally, we provide a free certified and supported solution for OT environment. All the information about the demo can be found in specific GitHub repo. Thanks again for your time today.